Hello everyone, in this video we'll be observing the necessary mathematical framework for the amplitude modulation and then we'll be taking up few brilliant questions. Okay, if someone asks you what do you mean by the amplitude modulation, what should be your answer? Amplitude modulation means varying the amplitude of the carrier signal in accordance with the message signal. At each instant, the amplitude of the carrier varies according to the information or the message signal. Okay, and why do we need modulation? For that, we have a detailed video in the same playlist. You can watch that. Usually, to extend the range of the communication, we use the modulation. I am taking up a practical example. Suppose there is a letter which has to be delivered 200 kilometers away. Now, if you throw the letter, will it go directly to that location? Not possible. In the old times, people used the pigeon for that thing. The pigeons were the carrier and that letter was the message. I hope you understand this analogy. The carrier should have high energy, high frequency as compared to the original message signal. And then that carrier can carry the signal to a great distance. Got it? Taking up another analogy. You see this Aladdin and the carpet here is serving as a carrier. If you treat Aladdin as a message which has to be delivered to a great distance, then carpet has high energy, high frequency. It can carry the message to a great distance. I hope you got it. Another famous analogy is the Harry Potter. Look at the Harry Potter and the broom. Now, can you figure out which is the message and which is the carrier? Correct. The broom is the carrier. It can carry the Harry to a great distance. I hope you understand it. Okay. Now, we are starting the mathematical framework. So, pay attention on the board. Here, we are taking up the message signal first. We will write this as MT, which will be equal to AM sine omega MT. Okay. AM is the amplitude of the message signal, omega m is the angular frequency of the message signal. Then we write the carrier signal. We indicate the carrier signal as CT. It will be written as AC sine omega CT. One thing we should keep in mind, the carrier should have great energy, so it can carry the message signal to a great distance. It means the omega C must be greater than the omega m. Do you agree? Or this omega c can be written as 2 pi fc. Fc is the carrier frequency. This omega m can be written as 2 pi fm. Fm is the frequency of the message signal. Okay. Now I am writing the expression of the amplitude modulated signal, which we will write as CMT. And this will be equal to AC plus AM sine omega mt sine omega CT. I am explaining why we are doing this. In amplitude modulation, we have to vary the amplitude of the carrier in accordance with the message signal. It means the AC has been chosen as the reference and the amplitude of the carrier is varied according to the message signal. Okay. So in AC, I am adding up this entire signal and then the sine omega CT is kept intact. This is the amplitude modulated signal. Got it? Here you can treat this as the amplitude of AM signal and this will give you the frequency of the AM signal FC. Now let's carry further the derivation. The CMT, I am taking out AC from the expression here. So it will look like 1 plus AM by AC sine omega MT and then sine omega CT. Okay. This AM by AC is given a specific name. We call it modulation index. Mu is equal to AM by AC. Sometimes they call it depth of modulation also. Simplifying it, it will be written as AC sine omega CT plus mu AC sine omega MT sine omega ct. Okay. Any device which is producing AM signal should be capable of multiplying the message signal and the carrier signal. This is the characteristic of the any AM signal. Okay. Now sine A, sine B kind of format you can see here. This I am treating as sine A and this I am treating as sine B. Utilizing this formula we can put up the data again here. Do you agree? This has been rewritten in this format and I am simplifying it further. AC sine omega ct. This mu AC, from here you can write mu AC is equal to AM. So AM by 2 cos of omega c minus omega m and then t minus AM by 2 cos of omega c plus omega m and then t. This is the final expression for the AM signal CMT. So if someone asks you which frequencies are present in the AM signal, this one omega c as well as omega c minus omega m as well as omega c plus omega m. If you have any doubt in the derivation, you should fire up the chat box. I'll reply. And if you have no doubt, I'll go further and I'll plot the graphs of all these things so you can better visualize this signal. For that, we'll be utilizing this space. First of all, we'll be plotting the message signal. Amplitude of the message signal is AM and it's a sinusoidal signal. So we can plot it like this. Is it okay? Then we'll be plotting the carrier signal CT. Its amplitude is AC. Here we designate the level AC. And since the frequency of carrier is much greater than the message signal, it indicates that time period of the carrier will be much smaller as compared to the time period of the message signal. So while plotting it, we need to take care that time period of the carrier will be very less as compared to the message signal. Okay, pay attention. This time period is TM, time period of the message signal, and this time period starting here and then reaching here, this is TC. Time period of the carrier is much small as compared to the time period of the message signal. Okay, here the one cycle of the carrier has been completed. Done. Now the most important part of this entire calculation is plotting the AM signal, and for plotting the AM signal we'll be utilizing this expression. We have chosen the AC as the reference. So I'll designate the level AC. If this distance is AC, then here should be the level AC. Now you have to add the message signal. So this level is AC plus AM. How? Looking at the amplitude of the AM signal, the maximum amplitude of the AM signal will be AC plus AM when sine omega t becomes equal to 1. You get this? And the minimum amplitude will become AC minus AM when the sine omega mt becomes minus 1. Got it? Let's see it here. This length is AC, this height is AC, so here is AC. And in AC, we are adding up the AM. So this is AM, so adding up AM here, this is AC plus AM. And here is the level AC minus AM. Got it? Now, we have to plot the message signal again, because with the AC we have added up the message signal AM sine omega mt. Clear? And I am going to plot the message signal dotted. I'll explain why we are doing this. So starting from AC, I'll plot the message signal. We have to take up the mirror image of this. So that I am doing with the blue marker. In this envelope, we have to fill up the carrier signal. So see it here. I am explaining the things once again. We take the AC as the reference. The amplitude of the AM signal is given by this expression. When sine omega t is equal to 1, sine omega mt is equal to 1, then we get the maximum amplitude as AC plus AM. The lowest possible amplitude is AC minus AM. And then we have to plot this message signal. Keeping the AC as the reference, I have plotted the message signal. Then we take the mirror image of this message signal like this, and then we fill up the carrier wave inside the envelope. So this is the AM signal. Do you get this? Now, in oscilloscope, you can see the AM signal very clearly. And in oscilloscope, let's say this is the maximum voltage level. I'll indicate it here as Vmax. Done. And this voltage level we are going to write as V minimum. Then how much is V maximum? Look at this. The V maximum is equal to AC plus AM. We call it equation number 1. And how much is V minimum? V minimum is equal to AC minus AM. Is it okay? If you add the equation 1 and 2, what you will get? Speak up. By 1 plus 2, you will be getting the value of AC is equal to V max plus V minimum divided by 2. And if you subtract equation 1 and 2, you will get the value of AM. These values of AM and AC we can submit here. Then we'll get another expression for the modulation index as V max minus V min divided by V max plus V min. We'll be observing the questions in which they will give us the maximum voltage and the minimum voltage, and then putting that voltage will directly get the modulation index. Practically, this is how we determine the modulation index. The waveform is observed on the oscilloscope, and then Vmax and V minimum readings are placed here. Okay, I hope you understand this all. Once again, I am explaining everything because this part is pretty important, how we have done the things. First of all, we have taken up the message signal. Message signal is AM sine omega mt. So this is the amplitude of the message signal AM, and sine wave is there. Fine. For making the derivation simple, we have taken the phi 0 in both the waveforms, message signal as well as the carrier signal. Now we'll be plotting up the carrier signal. The amplitude of the carrier signal is AC, but its frequency is high. So the time period of the carrier signal will be very small as compared to the time period of the message signal that we can see here. Now, in order to plot the amplitude modulated wave, we will take the AC as the reference, this AC as the reference, and maximum amplitude of the AM signal will be AC plus AM when sine omega mt is 1. So this is AC plus AM. How I made it? This distance is AC, so this is AC. This is AM. In AC we have added up the AM, so AC plus AM. And from AC, when you subtract the AM, this is AC minus AM. Now you plot the message signal again, this message signal. Then you take the mirror image. Fine. Now the frequencies of LSB and USB are different, but they will be a bit close. Why? Omega C is much greater than the omega M. Let's say omega C is 10,000 and omega M is 10. Then 10,000 minus 10 and 10,000 plus 10 will be bit close to each other. Got it? And then this waveform can be observed on the oscilloscope. In oscilloscope, we can directly see the V maximum, we can directly see the V minimum, and then we can obtain the value of the modulation index. I hope you understand it. It's critical part, it's the most important part of this video. Although in order to explain this thing again, I'll take up another question with a digital signal and we'll do the same thing again, so you can get it in a better way. Right now, you can pause the video and you can note down everything. Then we'll be observing the details of the modulation index mu. Okay, note it down. Now let's see the details of the modulation index mu. Suppose we take up a case where mu is 0. Mu is equal to 0 means that the amplitude of the carrier varies 0% above its unmodulated level. This was the unmodulated level of the carrier, okay, AC, and it varies 0% above it and varies 0% below it. Means what you will be getting? You will be getting just a carrier wave, okay. So if you take mu is equal to 0 means AM is 0 and then your signal has only the carrier wave. This kind of signal can be sent or can be received, but it carries no information at all. Practically, if you want analogy, then this is like sending a pigeon without a letter. Pigeon goes from one location to another location but doesn't carries any letter, any message. Got it? So this is of no use. Then we take up another case. Mu is equal to 0.5 means 50% modulation. For 50% modulation, the amplitude of the carrier varies 50% above and 50% below its unmodulated level. Suppose the amplitude of the unmodulated carrier is 1, then above 50% means the carrier amplitude will go up to 1.5 and below 50% means the carrier amplitude will drop to 0.5. That is the meaning of the 50% modulation. Got it? This kind of modulation is counted as under modulation. Then comes the most important case, mu is equal to 1. Mu is equal to 1 indicates 100% modulation, and in this case there is the maximum power transfer by the antenna and there is the greatest voltage output at the receiver. Mu is equal to 1 means what? The amplitude of the carrier will vary by 100% above its unmodulated level as well as below its unmodulated level. In all practical systems, we try to keep the value of mu greater than 0 and less than equal to 1, and the best value of the mu is 1. Got it? Now let's talk about the last case of the modulation, over modulation. We consider, let's say mu is equal to 1.5 or 150-100% modulation. It means what? Above the unmodulated level of the carrier AC, the amplitude of the carrier will vary by 150% above and below. So this time the envelopes will cross, and when the envelopes will cross, there will be the distortion in the message signal. Okay, demodulating this kind of signal is bit complex. In these additional sidebands there occur the phase reversal. What I mean to say, you check this thing here and here. If you check, there is the phase reversal of the carrier wave. So that causes the distortions. Clear? Note it down. And one more thing I would like to tell you, sometimes the mu will be given in the percentage or will be asked in the percentage, such as if modulation index is 0.7, then the percentage modulation is 70%. And what do you mean by 70% modulation? The carrier will go up by 70% above its unmodulated level and will go down by 70% below its unmodulated level. Got it? Note it down, then we'll go further. Now we'll talk about the bandwidth of the AM signal. For that, we are plotting a diagram between frequency and the amplitude. First part of the AM signal is this carrier wave. Its frequency is indicated, let's say, by FC, and amplitude is AC. Then the next part is having the frequency Fc minus Fm. Okay, so Fc minus Fm will be plotted here, and its amplitude is Am by 2 or mu AC by 2. You can write anything. I am showing it here. This level will be mu AC by 2 or Am by 2. You can write anything. And the last part is upper sideband. Its frequency will be Fc plus Fm, and amplitude is Am by 2 or mu AC by 2. Okay. So plotting the upper sideband Fc plus Fm, and its amplitude is same as this one. Is it okay? Here you will get the bandwidth. The bandwidth will be given as Fc plus Fm minus Fc minus Fm. Is it okay? This is the bandwidth, and when you simplify it, what you will get? The bandwidth will come out to be 2 times of Fm. It's pretty interesting expression. The bandwidth of the AM signal is twice of the frequency of the message signal. Suppose the frequency of the message signal is 5 kilohertz. Then how much is the bandwidth of the AM signal? 2 into 5 kilohertz means 10 kilohertz. Is it okay? This is a nice information. You should note it down, and then we'll go further. Now we'll see the limitations of the AM. In the amplitude modulation, there is the variation of the amplitude of the carrier, and the amplitude of the noise is also picked up by the AM. So the reception quality of the signal is poor. Got it? So to remove this issue, the FM is used. In FM, there is the variation in the frequency, so it remains unaffected by the amplitudes of the noise signals. Okay. The second issue with the AM, it is power inefficient, because majority part of the power of the AM signal is taken up by the carrier signal. Very small power is allocated to the sidebands, and the message is actually contained in the sidebands. We know the formula of the power, RMS power I am talking about. The RMS power is equal to Vrms whole square divided by R. Here R is the resistance of the antenna. Let's say we are transmitting the signal through the antenna. Prms for the carrier signal will be Vc by root 2 whole square divided by R. Got it? Vc is the peak carrier voltage, and Vc by root 2 gives you the RMS voltage for the carrier signal. Done. Similarly, we can find the power for the LSB and USB. Then you can see it clearly that the power in sidebands is less than the power in the carrier. So the AM is power inefficient, and due to this inefficiency of the power, the range of AM is also limited. Signal cannot be transmitted to very great distances. So these are few issues with the amplitude modulation. Okay, you may note it down, and then we'll be taking up numerous brilliant questions to grasp the concepts very well. The first question is simple one. If you remember the derivation, you can quickly answer it. Which is missing? Looking at this, you can say the omega m is missing. Omega c is present in AM signal, omega c minus omega m is present, omega c plus omega m is also present. This individual omega m is missing. Simple. Note it down, then we'll be taking up the next question. This question is a good one, so I request you to pause the video here and try it once yourself, and then you can see the solution on the board. I hope you have plotted the AM signal. Let's see the solution here in detail. First of all, we'll plot the message signal. On the x-axis, I am taking up the time, and the message signal has the amplitude 1. This time we are using a digital signal. Is it okay? After the message signal, I'll be plotting up the carrier signal. In the carrier signal, if we look at the equation, the amplitude is 2 and this is 1 and this is 2. So 0, 1 and this level is 2. Same I'll do here. So let me plot the carrier first. The carrier is a sinusoidal wave starting from here, and carrier has a high frequency. This is how we plot the carrier. Computer generated diagrams will be much better. I'm just giving you the brief idea how to draw them. Now we should write the amplitude modulated signal. We indicate it as CMT. Got it? Again, I am taking the time on the x-axis. Take the amplitude of the carrier. This is 2. So 1 and 2. 0, 1, 2. Okay. This is the reference for the unmodulated carrier peak. Same we do here, the 1 and then 2. So this is 1 with the negative sign, 2 with the negative sign. Now in the unmodulated amplitude of the carrier, we are going to add the message signal. So there will be another one here, and this coordinate here I should write as 3. This level is 3, and the same thing I should do here. So level is -3. Is it okay? I am going to plot the message signal, but dotted. We call it envelope. Why we plot it dotted? Because the envelopes are imaginary actually. While doing the derivation, I told you we take the dotted lines for the envelope. The reason behind that, these envelopes are imaginary. Okay, they just connect the peaks of the carrier wave. Now you take the mirror image of this thing. Taking up the mirror image of this thing will look like this. Do you agree? Now it's time to fill up the carrier signal in the envelope. Done. I hope you made the similar things. Computer generated diagrams will be much better, but at least you got the idea. Note it down, then we'll go further. Here is another brilliant question. So again, the same request, pause the video here and give it your best shot. Then I'll be simplifying the things on the board. I hope you got the correct answer. The third option is correct. Why? Let's pay attention. If we look at the given picture, first of all, we can obtain the modulation index mu. Mu is equal to Vmax minus Vmin divided by Vmax plus Vmin. Do you remember how much is the value of Vmax given? Speak up. I'll be computing the things here. Vmax is 10. V minimum is 8. And here 10 plus 8. So it comes out to be 2 by 18, which is 1 by 9. So modulation index is 1 by 9. In which option you can find the modulation index as 1 by 9? Think about it. Okay. Processing the next information. The time period of the message signal is given as 100 microsecond. And we know one thing, that time period is 2 pi by omega m, which is equal to 100 into 10 to power minus 6. So this will give us the value of omega m. Omega m will come out to be 2 pi into 10 to power 4. Similar computation you can do for the time period of the carrier. Tc is given as 8 microsecond and it can be written as 2 pi by omega c. Omega c comes out to be 2.5 pi into 10 to power 5. So now you can check in which option these values are getting satisfied. There is a single option, third option. Got it? Easy but nice question. So note it down, then we'll go further. Here is another interesting question. An AM signal is written here and we have to find the sideband frequencies in kilohertz, the lower sideband and the upper sideband. Give it a try, then I'll be simplifying it. Let's see the solution here. This data is higher, so it should indicate the omega c and it must indicate the omega m. Do you agree? Because in our original derivation omega c was greater than the omega m. Okay, now I can start the solution. Omega m is equal to 2 pi fm and this data can be written as 22 kilohertz. Do you agree? Because we need the options in kilohertz, so I am writing the data in that format. We know that pi is equal to 22 by 7. Submit that value of pi here. You will get the fm is equal to 3.5 kilohertz. Same computation I am doing for omega c, which is 2 pi fc, and if you check this data we can write it as 550 kilohertz. Again put up the value of pi and compute the fc. Speak up, what is the value? It comes out to be 87.5 kilohertz. Done. You can do that fc minus fm. 87.5 minus 3.5 kilohertz, which is equal to 84 kilohertz. Okay, and the upper sideband will have the frequency fc plus fm. fc plus fm you can easily do 87.5 plus 3.5 and the answer is in kilohertz, so 91 kilohertz. And what if someone asks you the bandwidth of the signal? Bandwidth of this signal is equal to 91 minus 84 kilohertz. Got it? It is equal to 7 kilohertz. Could you find that bandwidth directly? Yes, it's easy. The bandwidth of the signal is twice of the FM and this is twice of the FM. Okay, simple and easy question. Note it down and then we'll go further. It's an easy question. You can answer it. The correct answer is either you send the omega c minus omega m or you send the omega c plus omega m or both. In all three ways the message signal can be retrieved. For example, if you send only this, it contains the omega m and using some mechanism the message can be retrieved. If you send only this, it also contains the omega m. Using some technique the message signal can be received, and if you send both, even then the message signal can be retrieved. Got it? Note it down, then we'll take up the next one. It's an easy question, so I request you to give it a try. Pause the video and then post your opinion in comment box, and I am simplifying the things on board. First of all, I am obtaining the modulation index, which is written as mu is equal to AM by AC. Here amplitudes are given in the term of voltage. The amplitude of the message signal is how much? 10 volt. Amplitude of the carrier signal is 20 volt. So mu is equal to 1 by 2 means 0.5. Okay. If someone asks us how much is the percentage modulation, that is also simple. it will be equal to 0.5 into 100%, which gives you 50% modulation. Next computation. How much is FC? FC is 1000 kilohertz, looking at the data of the question. And how much is FM? FM is 10 kilohertz. Okay, so the upper sideband comes out to be 1010 kilohertz. Now we go for the lower sideband. It will be equal to FC minus FM. It is equal to 1000 kilohertz minus 10 kilohertz. So we get this as 990 kilohertz. Do you agree? Then bandwidth is pretty simple. 1010 minus 990 kilohertz, which is equal to 20 kilohertz. Can we obtain this bandwidth in another way? Yes. Another formula of the bandwidth is 2 times the frequency of the message signal. Frequency of the message signal was 10 kilohertz. So it is 2 into 10 kilohertz. That also leads to the same answer, 20 kilohertz. Note it down, then we'll go further. Here is the simplest possible question. Just looking at the language of the question, smart students can speak up the answer. Tell me, what is your answer? Mu will be 2 by 3. How? Let's have a look here. We know the formula of the modulation index. Mu can be written as Vmax minus Vminimum divided by Vmax plus Vminimum. Okay. How much is the maximum voltage in this question? 15 volt. Minimum voltage is 3 volt. Maximum is 15, minimum is 3. So it is 12 by 18, which comes out to be 2 by 3. Simple. Okay. I hope everyone got the correct answer. Note it down. Then we'll go to the next question. It's another easy question. You can do the calculations and quickly post your answer in comment box. Okay, the correct answer is 9 volt. See how to do the calculation. Question is telling us 75% modulation. It indicates that mu is equal to 0.75. Do you agree? We know the formula of mu. Mu is equal to AM by AC. Mu is given as 3 by 4. AM is unknown. AC is given as 12 volt. Then it provides you the value of AM as 9 volt. Okay. Simple answer. Note it down. Then we'll go further. It's another simple question. So I request you to pause here and give it a quick try. I'm waiting for your answers. The correct answer is mu is equal to 0.6. Actually, looking at the data of the question, we get the idea that we should be using this formula. Mu is equal to Vmax minus Vmin divided by Vmax plus Vminimum. Is it okay? Maximum voltage is given as 160. Minimum voltage is 40 volt. 160 plus 40 volt. When you do the computation, it gives you mu is equal to 0.6. Clear? Note it down. Then we'll move to the next one. Another nice question. So you can give it a try and then you can match your solutions with the board. Okay, I'm simplifying the things here. First of all, looking at the diagram, we can obtain Vmax will be equal to 100 by 2, which is equal to 50 volt. Do you agree? The Vminimum will be equal to 20 by 2, which is equal to 10 volt. If we know these values, we can easily find the percentage modulation, which will be equal to Vmax minus Vminimum divided by Vmax plus Vminimum into 100%. Okay, that will be our first answer. So I am putting up the data. V max is 50, V minimum is 10 divided by 50 plus 10 into 100%. Do the calculation, it will come out to be 66.67%. Okay. Now we have to find the value of Vc and Vm, the peak voltage of the carrier and the peak voltage of the message signal. That computation I am doing here. For second part, we know the formula. Vc is equal to V max plus V minimum divided by 2. So I am putting up the values. V max is 50, V minimum is 10, and this divided by 2 gives us 30 volt. Okay. This is the peak value of the carrier signal, peak voltage. Then we need the peak voltage of the message signal. Vm will be equal to V max minus V minimum divided by 2. These things we have seen in the derivation, if you remember. So now I am feeding up the values only. 50 minus 10 divided by 2. So this answer comes out to be 20 volt. You can note it down, then we'll be taking up the next question. Another simple question, and you can orally answer it. Calculation is simple. Okay, the answer will come out to be 10 stations. How? Let's see it here. The number of stations will be technically equal to the total bandwidth divided by bandwidth per station. Total bandwidth is given as 100 kilohertz and bandwidth per station required is 10 kilohertz. So the answer is 10. Is it okay? Now how we can see it? Suppose this is the 100 kilohertz bandwidth. The first station takes up the 10 kilohertz. Then the next station takes up another 10 kilohertz. And in this way, how many stations can be accommodated? It's simple. In this way, we can accommodate totally 10 stations. Is it okay? Note it down. Then we'll be taking up a question on the similar pattern. It's another simple question, so you can give it a try, and I'm simplifying it on the board. We know the formula. Total number of stations is equal to the total bandwidth divided by bandwidth per station. Do you agree? Now, the total available bandwidth is 10% of 10 gigahertz. 10% of 10 gigahertz. Do you agree? Divided by the bandwidth per station is 5 kilohertz. 5 kilohertz. Okay, the unit hertz will get cancelled out. This will give us the answer 2 into 10 to power 5. It's a great number. It indicates what? If the total bandwidth is higher for the transmission medium, then you can have a great number of stations operating simultaneously. Okay, note it down, then we'll go further. Another nice question. So you may pause here and you can give it a try, and then I'll be simplifying it. Let's see the solution here. First of all, we'll obtain the frequency. We know one formula, C is equal to F lambda. Using this, the F will be equal to C by lambda. We'll put everything with the proper SI unit. So C is 3 into 10 to power 8 meter per second. Lambda is 800 into 10 to power minus 9 meter. Got it? This gives us the frequency 3.75 into 10 to power 14 hertz. Is it okay? Now we know the formula of the total number of stations. Many times we have used it. the total number of stations will be equal to the total bandwidth divided by the bandwidth per station. More you write, better you will understand. So I request you to write all these things simultaneously. Total bandwidth can be computed. According to the question, we use 1% of this. So 1% of this means 1 by 100 into 3.75 into 10 to power 14. Okay. And bandwidth per TV station is 6 into 10 to power 6 hertz. The unit hertz will get cancelled out. If you wish, you can skip it. Done. This gives us the total number of stations, which is equal to 6.25 into 10 to power 5. Again, it's a great number. So operating at very high frequencies, we can simultaneously transmit many television channels. Done? Note it down, then we'll go further. Here comes the last question of this video. So I again request to pause here and give it a try. It's a beautiful one. I hope you all have chosen the correct answer, which is 2000 kilohertz. How? Let's see it here. According to the question, FM is equal to 10% of FC. The message signal or the information signal is also known as the modulating signal, and according to the question, the frequency of the modulating signal is 10% of the frequency of the carrier signal. Okay, this is given as 250 kilohertz. 10% means 10 by 100. Okay, this computation gives us the value of FC as 2500 kilohertz. Another information we require in this question is the bandwidth. Bandwidth is twice of the FM. Do you remember? And FM is available. It means the bandwidth here is 500 kilohertz. Now, using these informations, I am trying to plot a picture. Let's say we write the carrier frequency here, which is 2500 kilohertz. Okay, here will be the lower sideband and this should be the upper sideband, and this bandwidth is 500 kilohertz. Is it okay? It means how much should be the frequency here? 2250 kilohertz. How much should be the frequency here? 2750 kilohertz. This is our old station. Now suppose we want to allocate the bandwidth for a new station. Then that new station, I am indicating with the red color. For the new station, let's say I take up the frequency here as 2000 kilohertz. The bandwidth of the new station is also 500 kilohertz, and then you can check up the things. 250 kilohertz in this direction, you'll reach here, and then again 250 kilohertz in this direction. In this way, the new station and the old station can operate together without any interference. I hope you understand it. It was a simple and nice question. You may note it down, and then you'll be getting the important points of this chapter. I hope you all enjoyed this video and got the concepts very well. On the screen, I am presenting the important points of the entire video. Okay. After this, you'll get a checkpoint that I request you should try yourself. And the answer of the checkpoint can be verified at the end of this video. Stay awesome. See you again. And if you want any other topic, let me know in the comment box. Bye-bye.